we're going to look at representing functions as power series. And to start with, we're going to look at the geometric series AR to the K minus 1, that sum, which is AR squared, and this goes on indefinitely. Knowing what we already know about geometric series, we know that if the absolute value of r is less than 1, this will converge, and it will converge to the limit of a over 1 minus r. So we're going to take this as our basis, and from this we're going to create a special geometric series that's a power series. We're going to look at the series as n goes from 0 to infinity, x to the n. And if we write this out, the first few terms, it's x to the 0, which is 1, x to the 1, x squared, x cubed, and this will go on and on indefinitely. This is actually a geometric series, and in this case, the a value in this series, a value is 1, and each term keeps being multiplied by x, so the r value is going to be x. And we know that this will converge if the absolute value of x is less than 1. That will tell us that the limit of this geometric series, if it converges with absolute value x less than 1, is a over 1 minus r, which is 1 over 1 minus x. What we have just determined is that the series, as n goes from 0 to infinity, x to the n, which is the sum of these unit polynomial terms, converges to the function 1 over 1 minus x. So this infinite series is the representation of the function 1 over 1 minus x. We're now going to use this result to create many other series representations of functions. I can write this so you can see that the series 1 over 1 minus, in this case x, I'll put a box to represent x, is just the series 1 plus that x, which is box, plus box squared, plus box cubed, plus box to the fourth. And this will go on and on indefinitely. So this is the generalization of any function 1 over 1 minus something is going to be this infinite series, which can then be written as n going from 0 to infinity, box to the nth power. Given this, what we want to do, for example, I'll say, given the function f of x is x over 1 plus 2x, I want you to write it as a power series. So I want the power series representation for this function. To start with, I'm going to look at the function 1 over 1 plus 2x. I want to put that in this series representation. But this has a negative here, a minus, so I can write as 1 minus something. I can get that if I put a negative 2x in here. So that means if I put negative 2x here, I will get, substituting negative 2x for the x's, negative 2x, negative 2x, negative 2x. If I do that everywhere here and the same here, I get the series representation for the function 1 over 1 plus 2x. So this will be 1 minus 2x plus 2 squared x squared minus 2 cubed x cubed plus 2 to the fourth x to the fourth. And this is going to go on indefinitely. And I can write this now in series form like this. 0 to infinity, negative 2x to the n, which can be written as negative 1 to the n, 2 to the n, x to the n. I don't have f of x. I need the x on top. So I'm going to have to multiply x times all of this, which means I'm going to have to pull an x in there through this. In doing that, this series, x over 1 plus 2x, I'm just going to distribute the x through. It becomes x minus 2x squared plus 2 squared x cubed minus 2 cubed x to the fourth, and this will go on indefinitely. Let's look at the next page in a minute and we'll see that. Looking at that, pulling and distributing the x through, this will be the series as n goes from 0 to infinity, negative 1 to the n. We've got the x, then we've got the 2 to the n and the x to the n. And sure enough, we can put the x and the x to the n together. And that's the series. Negative 1 to the n, 2 to the n, x to the n plus 1. We now have the series representation for the rational function f of x being x over 1 plus 2x. What we have is this one result that the function 1 over 1 minus box, if we think of it as this series, this infinite power series, we'll be able to substitute different expressions in the square, in the box, and that's going to give us the function of simple rational functions. So we're going to use this. This is what we use for all our problems. As a second example, we're going to take we know the function 1 over 1 minus x. That's one of the basic ones that we're using, that basic geometric series. We're going to look at the antiderivative of that. And looking at the antiderivative, we know that it's a u substitution. U is 1 minus x, so negative 1 du is dx. So this becomes negative the log of 1 minus x. I want you to find the series, that is power series representation for the function f of x is the log of 1 minus x. So for this, we know that 1 over 1 minus x is 1 and x squared. This is going to go on indefinitely. To get the negative log, we take the antiderivative, so we are going to take the antiderivative term by term of the power series. So we take the antiderivative of 1 is x. The antiderivative of x is x squared over 2. The antiderivative of x squared, x cubed over 3. The antiderivative here, x to the fourth over 4. And this is going to go on indefinitely. And we know that this was negative the log of 1 minus x. But to get what I want, I'm just going to multiply this by negative 1, which means this series is multiplied through by negative 1, so the log of 1 minus x, I just multiply negative through. So it becomes negative x squared over 2, negative x cubed over 3, negative x to the fourth over 4, and this is going to go on indefinitely. Now we have to put this in, this is sometimes called closed form. So if I start at 0, the closed form for this, so this will become negative 1 x to the n plus 1 over n plus 1. That's called the closed form of that function. That's the actual series form for that function. As an offshoot of this problem, now I have the series representation for log of 1 minus x. And suppose I want you to use this series to find the value of natural log 2. In order to have log 2 from this, it's the same as log 1 minus x. So 1 minus x would have to equal 2, so negative x would be 1, so I would have to let x be negative 1. So that means everywhere I have x, I'm going to replace it with negative 1. This tells us that the series representation for the number log 2 is everywhere I have x, I'm going to put a negative 1. So it's minus negative 1 minus negative 1 squared over 2 minus negative 1 cubed over 3 minus negative 1 to the 4th over 4. And these are going to go on indefinitely. And this is, using this closed form, the series minus 1 to the n plus 1 over n plus 1, as n goes from 0 to infinity. But this becomes the series, this is 1 negative 1 and n plus 1. It is negative 1 to the n plus 2 over n plus 1. If I wanted to, I can see that this series, if I did negative negative 1, it's 1. Minus a minus 1 squared is positive, so it's minus a half. Minus a minus is plus a third. Minus a positive, minus a fourth. So we have that log 2, if we continue with this, is actually a series we know. We know this as the alternating harmonic, and so we have just shown that the alternating harmonic series converges to the value of log 2. As an offshoot of this problem, we can use the alternating series result, and that result will help us to estimate the value of log 2. Let's say correct to 3 decimal places. We'll go to the next page for that. This alternating series result says if we have the alternating series, n goes from 1 to infinity, b sub n, and b sub n plus 1 is less than or equal to b sub n for all n, and the limit as n approaches infinity, b sub n is 0, then the alternating series result says the difference between the nth partial sum and the limit is less than the very next term in that alternating series. And of course, that's where the limit is s. So we have to show that log 2 minus the nth partial sum is less than the very next term. So in our series here, we know that b sub n plus 1 is 1 over n plus 1. That's our series. And we have to show that that is going to be less than 3 decimal places is 0, 0, 0, 5. So we invert this and we get n plus 1 greater than, because it changes the order, 1 over 0.0005, which is 2,000. So we get n plus 1 is greater than 2,000. And then, of course, subtracting 1, we get n is greater than 1,999. What that's telling us is that if we added up the first 1,999 terms, we would get a value of log 2 correct to 3 decimal places. So what this is saying is that log 2 is approximately 1 over 1 minus a half plus a third minus a fourth, dot, 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 and we go to this 1 over 1,999. If we sum all that up, its difference from log 2 is less than 0.0005. So it's correct. This sum is correct to 3 decimal places.